done. The other online classes that I have, there's only like one or two assignments.
All right.
So, yeah, that's the.
Let's do a little review on equilibrium. Hopefully, after the trauma of kinetics, equilibrium will be easy. Hopefully. So, review documents. Any specific problems that you want to tackle first?
I was looking over it this morning. I mean, at least 3.
Number 3?
Yeah, to understand number 3.
Okay. All right. So our equilibrium system is this. There are a couple of gases. And making a couple more gases. Let's see. Carbon, 2 oxygen. Yep. Okay. That's good. And the enthalpy of this reaction is which means what? It's endothermic. Right? It absorbs heat. Okay, so we're also given the K value at 1260 K. So if we're given the K value, then it's got to be equal to something. And since it doesn't say, it doesn't give you a subscript for K, you assume that it's a KEQ, which usually means that the concentrations are in molarity. Like that. And then the value is 1.6. And let's, just to be thorough, 1260. Okay. So if you put the same amount of each one of these gases, it says 0.15 moles in a liter, which means each one is that molar, right? Moles per liter. Now, we may not need all this information, but it is given, so I'm going to put it up there. Then the question. As the system comes to equilibrium, let's see. Okay. So if we're starting out with equal concentrations of each one, and they're each 1 mole, 1 to 1 to 1 to 1, then where does that leave the system in terms of it's not at equilibrium yet, right? So how do we know which direction it's going to go? If it were at equilibrium, you know, we could make some generalizations about it. But it's not at equilibrium, so what do we have to do? Have we calculate? Yep.
Yes, but we basically just calculate when we add them all together, like the CO.
Calculate the Q.
Yeah.
Q tells you which direction it's going to go. All right. Okay. So the Q is the same format as these guys, only we put in values that are not equilibrium values. So each one is right, because each one is the first power. We can do that in our head, can't we? It's equal to 1. So which direction does it go if we're equal to 1?
When I get up.
Right, Q then is less than K. So it goes to the left, doesn't it?
Oh, yeah.
Let's check it out, see if that's true. All right, so if this is less than that value, that means we've got less of this than we need, because it needs to be bigger. We've got less, oh no, it's the other way. It's that way. If this is less than we need, it needs to get bigger. That means we need more of that, right? So the reaction goes that direction. Goes to the right.
When you do Q,
Mhm.
is it still, like, would it still be the products over the reactants, or would it be the reactants over the products for Q?
It's always the same.
It's always the same? Okay.
Yep. Okay, let me say that again. Since this is smaller than we need to be at equilibrium, that means we have less of products and too much reactants. It makes this whole expression smaller, which shows that it's less than 1.6. So in order to get to 1.6, this has to increase, this has to decrease. So if that decreases, this increases. All right, so let's see which one satisfies. The temperature would, okay, we're going to look at the temperature first. So if it's endothermic, that means energy is on this side, goes into the reaction. So if it goes into the reaction, heat's being absorbed into the reaction, temperature would decrease. Right? So A and B are possibilities. C, D, and E remains constant or increases. Can't happen. Not in an endothermic reaction. So it's either A or B. So now we look at the second part. The mass of CO2 would increase. No, that means it go this direction. Right? So it can't do that one. There's got to be B. The temperature would decrease and the mass of CO2 would decrease. Okay. That's what I get for not memorizing QK relationship. I always reason it out. That's less than that, so the only way that could be is it's too small. That's too large. Okay, that was number 3. Let's see. I'm going to check them off as we go so I don't backtrack. Okay. That's the only one bothering you?
Mainly calculation ones would be mine,
Okay.
and maybe some like information.
Let's see. Well,
Did you remember 8 too?
sure. Number 8. So the question below refers to the equilibrium system. We got this equilibrium system. and that's pink. And then we add chloride to it. That's in equilibrium with this system. Well, the whole system actually. In equilibrium with these products. Okay, and this is blue. Okay. This is what's known as a coordination complex. In other words, you'll have the cobalt in the middle. And these 6 waters will be positioned around it some form or other. And they're bound reasonably tight. They're not covalent bonds, but they're tighter than just water floating around. And then when we introduce chloride ions, the chlorides displace the waters, and the waters become free, and that's how we see the color change from pink to blue.
That's supposed to be, okay. So the chlorine is what's making the change then?
Yeah, it's actually, it's the spectral absorption characteristics of cobalt that change when it's associated with water versus when it's associated with chlorine. Okay. That changes the way it absorbs light. Okay, when cobalt-2 chloride is added to pure water, cobalt-2 chloride, added to pure water, this ion hydrates. Yes, that's true. The hydrated form then reacts with chloride to set up an equilibrium shown here. Okay. So number 8 is, which statement below describes the change that the system will undergo if hydrochloric acid is added? Right, so if we add hydrochloric acid, we know that it's going to go completely to these 2. So this refers to, what we're talking about here is the common ion effect. So what 2 ions do they have in common? Well, what ion do they have in common is chloride. So when we add chloride, we're increasing this. So that should drive the system to the right. And let's see, it should become more blue. That's true. Yeah, A is true. It should become more pink, but it can't have it both ways. The equilibrium will shift to the right. That's true. Or to the left. Wrong. So E, yeah, 2 of these, A and C. E refers to A and C.
So we just have to take the acid and figure out what it would break into as far as ions go.
Mm-hmm.
Yeah, from there, just compare it to the equilibrium it gave us.
Right. You could probably get the same result with any chloride because all chlorides are soluble, almost all. Okay. As long as the chloride is soluble, you will produce the same effect. Assuming that you didn't add some metal here that would set up a competing reaction with water.
Now, is there any way that it would shift to the left? Like what would make that happen, like in this situation?
Okay. How would we shift it to the left? Well, it's unlikely that you can add enough water to do that. Right, because you're in aqueous solution.
So it has to be an outside source. Right?
You would need something that would remove chloride from the reaction.
Okay.
Right. So my suggestion would be something that forms an insoluble chloride. Right. And the first one that comes to mind is silver. So if you have silver ions, usually introduced with nitrate, silver nitrate, this silver and chloride would form a solid. Remove it from the reaction mixture, and then that would drive it back this direction.
Okay. All right.
Yeah. That's called a coupled reaction.
I heard that something like that, but
In your method?
Yeah.
Yeah, we're going to do that today.
pink, more pink, you can. Oh, crap. I read last time it was, pink. It's more hydrogen bond, something in there that's more hydrogen ions.
Oh, you're talking about acid-base reaction.
Yeah, where it turns pink.
Yeah, that's a little different. Where you had phenolphthalein. Yeah, you're measuring, if it's basic, it'll be pink with phenolphthalein. If it's acidic, it'll be clear.
Look at 12.
Okay. Check that one off. Let's see. Consider the reaction. Let's see. There's a gas, there's another gas. Gives rise to a gas, plus another gas. Oops. Wrong. There we go. You have gases A, B, C, and D at equilibrium. Okay, so we're starting at equilibrium. Upon adding gas A, the value of K does what? Let's see, we're going to add A. Let's add some of that. What happens to the value of K? What is K?
Isn't K temperature?
Mm-mm.
Or constant?
Not in this case. We have to identify it as a temperature in order for K to be a temperature. In this chapter, K is equilibrium constant. Doesn't matter what you do, K is still constant. Well, I take that back. It does matter what you do. If you change the temperature, K changes. But it didn't say we change the temperature. It just says we add A. K doesn't change. It's a trick question. It's an equilibrium constant. It's constant for a reason. If you don't change the temperature, K is constant. If you change the temperature, yes, you will get a change in K.
D, right?
Yes, D does not change as long as the temperature is constant. Check that one off. Well, let's see. Any others? I have some ideas, but I want to let you guys direct the review. Okay. Ammonia is prepared industrially by the reaction here. This is the Haber-Bosch process. The reaction that allowed Germany to propagate World War I after we embargoed all their bird and bat oil. They had to figure out a way to make their own ammonia. And let's see, for this reaction, enthalpy, standard enthalpy is minus 92.2 kilojoules. And K is K at 25. C is 4. 8. Okay, So those are the conditions at 25 degrees. So if we go from T25 to 500, is it? 500. See, which of the following is true? All right. So A says K for the reaction will be larger at 500 than at 25. K increases. B, at equilibrium, more ammonia is present at 500 than at 25. Ammonia. Let's do it this way. That increases. At equilibrium, this value is higher at that change temperature. Product formation. Is not favored as the temperature is raised. Product formation is favored. Okay. N2 with H2 to form ammonia is endothermic. And E, none of the above. All right, since we got none of the above is true, we have to eliminate everybody. Let's start with the easy one. That one right there, endothermic. Is that endo or exothermic? Exothermic, right. That one's out. Okay, as we go from, so let's put it where it needs to be. If this is exothermic, that means we have heat on this side, right? It's a product. Okay, so if it's a product, but it's not included in the K calculation. So K then would be what? K is ammonia squared over nitrogen to the first power of hydrogen, third power. Okay? So if we increase the temperature, what's going to happen to this? If we add heat, it's going to go like that way, isn't it? Because this is a product. Sorry. If heat's a product, and we increase it by increasing the temperature, we're going to drive the reaction back this way, which decreases this and increases that. Okay, so that means K will actually decrease. Puzzled looks. We'll say it again.
When you're increasing the temperature though,
Yeah, I thought
you'd increase it from the left, right? Like the left side, you'd increase the temperature on because that's what you're reacting, and then like what comes out would be the same, or like how does?
Well, no, it's at equilibrium.
Oh, okay.
Yeah.
But that's what I mean though. Like if you change the temperature at equilibrium, then wasn't that like? I don't know.
If you-
I don't get it.
Right. If you increase the temperature of the reaction vessel, it affects both sides.
Okay.
It doesn't just focus on that side. Heat is being applied to the entire reaction system. Right? So the key here is to find out where is the heat input. And in an exothermic reaction, heat input is on the product side. So we're increasing this value, which drives the reaction backwards.
Okay, so you're increasing the heat that was already there because of it being an exothermic reaction, which is causing it to go back the other way.
Right.
Okay. All right.
Yeah. We're good?
Yeah.
Okay. Okay, so that one doesn't work. It would actually decrease K. How about this one? Ammonia would increase. Well, it's corollary to what our discussion here. Ammonia can increase if we're going back that direction. It has to decrease. So really, this is our last option. Product formation is disfavored. That's true. That's going back toward reactants makes less product. And that was the problem that Fritz Haber had when he was trying to make ammonia with this reaction. He understood the reaction to be exothermic. And he knew he was juxtaposing equilibrium with kinetics. He knew that if he increased the temperature, he would get more impacts among the nitrogen and hydrogen molecules, right? So there's more potential for reaction. The problem is that the equilibrium situation said that even with those impacts, you're favoring this way, right? So his solution, add a catalyst. And the catalyst then would favor the production of ammonia in spite of the equilibrium. In other words, the equilibrium would still be valid, but the equilibrium position would increase the amount of ammonia you have, right? It's the difference between the K equilibrium and the equilibrium position. And the catalyst gave him more of this. Not a lot more, right? It could go through one reaction cycle and maybe get 10% product, which was an improvement over non-catalyst. So then what would he do? Well, the goal is to get as close to 100% as possible, right? So what you do is they're all gases, but we know that the boiling point of this one and this one are very, very low. So you can cool the mixture down, and this one will become a liquid, and these two will not. Right? So that's what he did. He just constantly bleed off some of the reaction mixture, run it through a cooling cycle, extract the ammonia, take these two gases, send them back through. So after 5 or 6 cycles, he had his efficiency up to 90%. Of course, you don't make explosives with ammonia. Well, yeah, you do sometimes. But in those days, explosives were gunpowder and I think they had nitrocellulose by then. So you can make nitrates. So take your ammonia and react it with oxygen and make nitrates. Then you can make your explosives. Make nitric acid.
Is that how they ended up making like phosphorus? How that works? Like, because they had like, I don't know if it was World War II when it started or not, but they had like grenades that like when they exploded, it sent out like they called it white phosphorus, but I don't know what it was actually made of.
Yeah, yeah.
And it would just kind of like eat into your flesh more or less. But I don't know like what would cause that. Would that be a nitrate too, or would that be like
No, that's just pure phosphorus.
just phosphorus?
Yeah.
Okay.
You just the trick is to mount it in your artillery shell in such a way that it's isolated from air until it explodes.
Okay.
And phosphorus contact with air and anything on your skin too, both of them cause that violent reaction.
Is that why it like I guess eats away
Yeah.
and it burns there?
Yeah.
Okay.
Oh
Big
I watched
gas
it.
cloud.
yeah.
Big gas cloud. Ammonia.
Yellow
gas.
Yeah, phosgene. You think of it. Yeah. Oh yeah, World War II was bad for that stuff.
My dad, he was born on a naval base in Turkey, so I've been like raised watching war movies constantly.
Okay.
Learn stuff.
Yeah. Yeah, they were experimenting with humans there, with their weapons for sure. Now that was the chemical warfare. Probably more people were killed by the Maxim gun.
Well, that was like the fastest firing weapon for like over 100 years, wasn't it? Like, I mean, it
Oh
was
yeah,
like,
it was like 600 rounds a minute.
yeah, it's crazy.
Yeah, and I mean they were heavy as hell. But all you had to do with trench warfare, you just set them up in overlapping fields of fire, and let the officers on the other side send their men at you.
Is that they had set up in the pillboxes in Normandy? They had those then?
No, they had advanced quite a bit.
Okay.
By that time, they had the MG34, and let's say they had improved upon that. I'm not sure if they all were there in Normandy, but that was the what they call it, the buzzsaw, the German buzzsaw. It would fire 1,200 rounds a minute. It was so fast you couldn't hear the individual pops. Yeah, and at Normandy, they had their guns trained. They knew exactly where they would strike.
Yeah, they had the like the whole beach marked.
And the mortars and everything, they were just zeroed in. So it was crazy. Okay. What shall we do next?
21, okay.
21. All righty.
Basically, anything 21.
Okay. 21 and climbing. Okay, we're at 500K. Now, this is the temperature. 1 mole of gaseous ONCL. ONCL is placed in a 1 liter container. So we have 1 molar, right? 1 mole per liter. At equilibrium, it is 5.3% dissociated according to this equation. So we have 2 here. As a gas. And it makes this gas plus this gas. Okay. Determine the equilibrium constant. Okay, we're also given 5.3% dissociated. 5.3% dissociated. Okay. So in order to calculate the equilibrium constant, we need the expression. So we're going to have K is equal to NO squared chlorine, our products, and this squared. So in order to do that calculation, we need to know what each of these concentrations is. So what does 5.3% dissociation mean?
I mean, it's like
5.3% of that is gone.
yeah, right. Is it just it breaks apart, or is it like?
It converts from this to that.
Oh, okay.
Yeah. And it does. It breaks apart and rearranges. Because you've only got 1 chlorine per molecule here, but you need 2 over there. That's why you need 2 of these. So my guess is that the mechanism is impact between these two of those. And then it gives you that.
Okay.
So to make some sense of this, I think we need an ICE table. Initial, change, equilibrium, in order to figure out what values need to go in here. Okay, so initial, change, equilibrium. And these are associated with each one of those, right? That's our table. Then we got this one here, and we got these two here. Okay, so what's our initial concentration? 1 molar there. And we're starting off with 0 here, aren't we? As if we put that in a container. It's placed in a 1 liter container, and then it proceeds to equilibrium. So we know which direction it's going because there's none of this. So it's got to go that way. So we're going to have a certain amount of this. And if we got one of those, we have to have 2 of these to maintain our molar ratio, right? And that means we had to lose 2 of those. Right? It's 1 to 2 to 2. Okay. So now at equilibrium, we'll have 1 minus 2x. We'll have 2x here, and that's x there. Okay. So now, inserting these values with unknowns in here is not going to help us. If we knew what that was, then we could find out what x is. But we are given what x is in a fashion. We start off with 1 molar here, and it's 5.3% dissociated. Let me check that to be sure I'm reading it right. 5.3% dissociated. So that means that 5.3% of 1 molar is lost from this side, right? Okay, so 0.053 times 1 is that many molar that's lost from this side, and that's equal to our loss here, which is minus 2x. That's how much was lost, that much. Okay?
So 5.3 is how much is lost right there.
Yeah, 0.053.
So
This is the percentage of 1. Right, that's why I use 0.053. Because that's 5.3%. Is equal to minus 2x. So what's x? 0.0265 equals x. Okay.
Wouldn't that be a negative one?
That doesn't have to be. Well, actually, that would be bad. 2x is 0.053. X is equal to 0.02. So this is going to be 0.0265. 0.0265 molar. Now that we know what x is, this value then is going to be 0.053. And this is going to be 1 minus 0.053, which is what? 0.847. Is that right? Where's that 9? That's 9. Yep. Has to be 9. Excuse me. That equals our whole. So this is the concentration of that. This is the concentration of that, and this is the concentration of that.
You gotta plug that into
Right. Okay. We plug it into this. So we got, NO is 0.053. Squared. And then chlorine is 0.0265 divided by 0.947 squared. And let's see, I like to check myself to see if I did it right, or it at least agrees with the Q document. 0.053 squared. I get 8.3 times 10 to the minus 5. Yep, it agrees. I don't know if it's right, but it agrees.
I got different answer. I got to the negative third power. I got 8.3 times 10, but it's not 5, it's 3.
Did you leave out a, did you put the decimal in the wrong place?
I think it probably forgot a 0.
Yeah. Try it again. Anybody else do that?
Okay, yeah, I got it. Right. We put the 0 back.
Okay. That's 21. And let's see, how we doing on time? We're okay. Yeah, let's do 22. 22 looks like a challenge. Okay. Let's see. For this reaction below, let's put the reaction down here first. Calcium carbonate, solid. Calcium oxide. Where would I go to see that reaction on an industrial scale? About a cement plant. They grind up calcium carbonate, run it through a kiln, and calcium oxide comes out the back. And then they mix that into Portland cement. And then all you have to do is add water to it. And it absorbs water, but it also reabsorbs carbon dioxide from the air. And reconstitutes your calcium carbonate in the form you prefer. So you put it in a mold, right? And then it rehardens.
So basically, like trees bring in carbon dioxide and make oxygen. So cement, if you have a cement block or cement somewhere, it absorbs CO2.
Yeah, takes CO2 from the air. Okay, let's see. KP is given. So this is in terms of pressure. 1.16 at 800 centigrade. Okay. So what is this expression equal to? It's equal to that. Right? Because there's a solid and a gas. Solids don't count. In equilibrium expressions, solids and pure liquids don't count. Only gases and solutions. Right? So this means at that temperature and at equilibrium, this value is equal to 1.16 atmospheres. Because there's only one term in there. And this is in pressure, so 1.16 atmospheres is our concentration of CO2. Okay, that was first step. Ram 22. Here we go. So we're also given 31.3 gram sample of that. And we put it in a 10-liter container. So this is the mass. 10 liters is volume. And temperature is that value. Okay. And the question is, what percent of calcium carbonate will react? So what percent of calcium carbonate is reacting? So this is the whole. We want to know the part, what disappeared from that side. That is percentage, right? So this is the mass of calcium carbonate used divided by the mass of calcium carbonate total. That's what we're looking for. So how do we know? How do we know how much of this disappeared? We know what we're starting with, right? Can we tell how much was lost? What's the relationship here? This goes to that. And we know how much this, right? We know, we can tell exactly how much of that we produce, right? Because we've got volume, temperature, pressure. We got that one, that one, that one. That's a constant. Solved for moles. It's a stoichiometry problem. Once you find out how many moles of this, you can convert that back to moles of this, which then can be converted to mass of what was lost. Then we plug it in our equation. Okay? So N equals to PV over RT. Pressure is in atmospheres, that's good. Why is that good? Because this is liter atmospheres per mole K. Liters, that's good. Don't have to change that. R 08206 liter atmospheres per mole K. And then temperature. Okay, temperature is not in the right form, is it? So we need 800 plus 273 to give us K. Now we can solve for moles. So let's see, 1.16, 10, 0.0826, 800 changed. small number. Yeah, I think I did wrong. Let me change this one right now. 1073, right? Yeah, let's do that again. 1.6. Okay, so I get 0.1317 moles of CO2. Okay. Now we know how many moles of carbon dioxide. We can convert that to how many moles of calcium carbonate are required. We just need our conversion factor from the balanced equation. Right, the ratio is one of these to one of those. And so it's a difficult calculation. Calcium carbonate. Now we need to convert that to mass, right? Let's get rid of our moles. Leaves us with mass. So calcium carbonate, I think, is in the neighborhood of 40. No, calcium's 40. 4008 for calcium. And carbon is 12.01.
That's 16, but there's 3 of them, so it'd be
48.
48, yeah.
So I get 100.09. Okay. So that is, let's see if I still got it in here. Yep, there it is. Multiply. So I get 13.2 grams of calcium carbonate U. So if we plug it in here, 13.2 grams divided by 31.3 grams. 42.1%. Let's see if I came close. Right on the money. So what's the trick to this problem? The trick is to understand what the calculation is. This one right here. That's what it's looking for. This answers the question. So you really need to be satisfied that this is your target. That's where you're headed. Then you see, do I have the information I need? Well, yeah, we already got that. Right. Now we need this one. So how do we get that one? Well, that's why it's a stoichiometry problem. Because in order to find out how much was used, you need to find out what the product is. And the product is determined by this. Okay. That was 22, I believe. Yeah. Okay. About about 24. Let's see. How's your time doing? Okay, we're good. You may want to look at 24. What you thinking? Do we have a choice? Yeah, you have a choice. You can pick something else if you want. So nitrogen reacts with hydrogen. All right, here we are again. To yield ammonia. Right. So this is 2 here and 3 there. At 200 degrees centigrade in a closed container, so temperature equals 200 C in a closed container. 1 atmosphere of nitrogen gas. So this is 1 atmosphere. Is mixed with 2 atmospheres of hydrogen gas. And at equilibrium, the total pressure is 2.2. So the total pressure at equilibrium is 2.2 atmospheres. What's the partial pressure of hydrogen gas? So we're looking at what's this. And these are both at equilibrium. So is that everything we're given? Yes. All right. Okay. Since we're given starting conditions, and starting conditions are 0 for that. So let's see what's going to happen during this reaction. It needs to be moved over a little bit. So let's say initial. Actually, initial's right there. Change and equilibrium. There we go. All right, so we know which direction it's going, don't we? Going that way. Okay, we want to determine what's the partial pressure of hydrogen. Now, did I miss? It didn't tell us what K was, did it? We may not need K. We do need to, for argument's sake, do that. Right. So this Kp is going to be partial pressures of these gases. So we're going to have partial pressure of ammonia squared, and then partial pressure of nitrogen to the first power, and then partial pressure of hydrogen to the third power. Okay. If we're headed for equilibrium, that's the condition that has to be met. All right. So we know the system is going to go that way. We just need to pick our unknown, our x value, if you will, so that when we solve it, when we solve for x, it gives us the partial pressure of hydrogen. So this is a case where you want to choose your x wisely. If we just said, we're going to lose some nitrogen, that's x. Well, if we do that, that means hydrogen is 3x, right? And then when we get ready to solve the problem, once we find x, we got to multiply it by 3, which you can do, and that's fine. But if we choose this x, we're going to lose that much x. How much of this shows up on that side? Well, 1/3 of that times 2. Right? How do I know that? Well, let's look at it this way. If we know if x is equal to the amount of hydrogen that was lost, x hydrogen, then what's our conversion? Right? 3 of these So this is going to be 2/3 x. That's where I got 2/3 x, okay? All right, so how about this one? This would be 1/3 x. Right? So for each x here, it only takes 1/3 of these to combine with it to make that. We good so far? Okay. So at equilibrium, we've got 1 minus 1/3 x. And here we have 2 minus x. You know what? Do you mind if I go back and start over? Because this is our equilibrium concentration right here. So who cares if we multiply it by 3, right? We're going to have to multiply it by something anyway. And subtract it from something. In fact, the fractional is the way I did it in the review document, work problems. But suppose we do make this x. So we're going to subtract some of that. That means we're going to lose 3 of these. And then we're going to add 2 of these. It's easier to follow it. Okay, so now we have 1 minus x. And this is 2 minus 3x. This is 2x. Okay? So, and this is the equilibrium situation. The equilibrium is 2.2 atmospheres. So, we're going to bring in Dalton here. Partial pressures. If this is the equilibrium pressure, then it has to be equal to that, plus that, plus that. Because they're all together in the same mix. So 1 minus x plus 2 minus 3x plus 2x equals 2.2 atmospheres. Okay? So let's see, let's combine all our values. Let's see, 1 plus 2 is 3. That's it. 3. And then minus x and minus 4x plus 2x is plus 2x left over. Are we good? 1, 2 is 3. Got that one. Minus x minus 3x is minus 4x. And then minus 4x and 2x.
Negative, wasn't it?
Yes, it would. There we go.
Okay. I was confused there for a second. I was like, I don't.
Okay, now we can solve for x. So let's take this one over here and that one over here. Okay. So this is what, 0.8. And x equals 0.4. Okay. That means this is 0.4 times 3 is minus 1.2. Equals 0.8. That's it. Let's see if that comes even close. Yep.
Where did the 1.2?
Okay.
You have to multiply it by 3.
No, 4. There we go. So 2 minus 1.2 is, well, that's where the 2 comes from. 1.2. Okay?
So it's B.
Yes. That was 24. Okay. We'll keep going. 25. They're all calculation types. Let's see. Oh, it's another ammonia. Okay, here we go. H2. Oh, we should have just left it up there. Now, what are we given? 2 moles of N2 in a 1 liter container, right? So it's molar. And 4 moles H2. Okay, that's that concentration. The equilibrium concentration of that is a value at 700 degrees. So the question is, what's our K at 700 degrees? 700. Okay. So our expression then is going to be, as before, squared hydrogen cubed nitrogen. So in order to calculate this, we need to find out what these values are. So these go into the mixture in the beginning, so that means there's none of that. All right. So this is our beginning situation. Then we're going to have change and equilibrium, and we need to find out the equilibrium in order to calculate the K value. What else are we given? We're given the equilibrium amount of ammonia, 0.55 molar. Okay? That's everything that we're given. We need to find values for these two in order to do the calculation. So let's see. If we end up with this much final, and we started with 0, that means we had to add that much, didn't we? That's the only way that we could get 0.55 out of this situation. Okay, now that we know that, we know where it came from. We had to subtract from these. Right? So if this is double, then single would be half of that, wouldn't it? For nitrogen, which would be 0.275. And if that's single here, then this is triple that, which would be 2, 2 and 6, 8. Correct? I did that right. 15, 24, 22, 2 and 6 is 8. Yeah. Let's see if I did this one right. So this one should be double that one. Let's see, that's 1 and 14. Okay. So now we calculate the equilibrium concentrations. This would be 1.725, is it? Subtract it from 2. Let's add back to make sure. 10, 10, 10. Yep. Then subtract this one. 297. 8 from 9, 1, 3. Let's be sure that's right. Okay. Question? Oh, okay. Ammonia, 0.55. Squared. Hydrogen, 3.175. Cubed. And 1.725 to the first power. So now it's just crunching numbers. Okay. So I get 5.5 times 10 to the minus 3. It jives with the answer sheet anyway. Okay. Let's do the last one on that page. Given the equilibrium constants for the following reactions. This tests your knowledge of transformation rules. That way. This is K1 for that expression. And then we're going to combine this one. And let's move it over some. Two. What's the K for the system? Okay, this is our target. We want to know what that K is. In terms of these two Ks, you look at your multiple choices, the value for this has to be written in terms of these two guys. Okay. So let's see if we got any transformations that are required. All right. So in order to get this one to go to here, remember Hess's law, where you combine equations? Okay. We got to match them up so that when we add them together, they give us this as our answer. All right. So how about this one? CuT2O. Copper's on this side, that's good. Oxygen's on this side, that's good. All right. But we need only 2 coppers. And we got 4 up here. All right. For this one, we need CuO on that side. So we're going to have to flip the equation. And that gives us 2 coppers on that side. So that should be okay. Just inverting it. So if we multiply this one times what to get 2 coppers? 1/2. What does that do to K2? If you multiply an equation by any factor, that factor becomes the power of the K. Right? So once we get this one down here, we'll just write it down here. 2Cu plus 1/2 O2. And then Cu2O. Then the K for this one, in terms of that one, is K1 to the 1/2 power. Okay? Now this one needs to be inverted. So if we write this one over here, Cu2O plus 1/2 O2 is equal to this one, 2. Now what does that do to the K? When you invert a reaction, you invert the K, right? Because now your products are reactants and your reactants are products. So you just take the inverse. So this one is going to be in terms of 1 over K2. All right? So let's see if that adds up. This is our target. We got 2 coppers. Yep. We got a 1/2 an oxygen and a 1/2 an oxygen. That's good. We got a C2O on this side and a C2O on that side. Cancel. And we got 2 copper 2 oxides on this side and 2 on this side. All right. So now, how do we combine the Ks for these 2 reactions? When you add 2 reactions, you multiply the Ks. So we multiply these together, and we get K1 to the 1/2 times 1 over K2, which is equal to K to the 1/2 divided by K2. Let's see if that's one of our answers. Looks like it's E. Okay. So this really is just a test of remembering the rules. Okay, we're okay. I'm going to give us about a half hour before we go into lab so we can talk about the pre-lab questions. Let's see how many we can do in the next half hour. Doesn't look like that already. Look at this one. Okay, we definitely like that already. That would be equal. Do 33 maybe. Got that one. Okay, so initial conditions. Temperature is minus 80 centigrade. The reaction is N2O4 gas yields 2 NO2 gas. Okay, and the K for that is 4.66 times 10 to the minus 8. Okay, I think we need an ice. We introduce 0.047 moles in 1 liter container. All right, so that means this is 0.047 molar. It's that many moles in 1 liter. And let equilibrium be established. So that means we start off with 0. The total pressure in the system at equilibrium will be. All right, so we're looking for total pressure. Since both of these are gases, and they're going to set up an equilibrium, in order to determine the total pressure, we need to know how many total moles of gas, right? Remember, if you know the total moles of gas and we're in ideal conditions, which we have to assume under these situations, then once we find the total moles of that and that, we can use the gas law to determine 33. We can use the gas law to determine the atmospheres, right? So with this relationship, and we know it's going that way, we're going to end up with, we're going to lose some on this side, and we're going to gain 2 on that side because of 1 to 2. Right? So overall, we got 0.47 minus x, and this is 2x. Okay? So, and this is molarity, right? So how do we find what x is? Well, we got k, so we need an expression for k, which would be NO2 squared divided by N2O4. And we plug in our values. Well, let's see. Let's plug in our values first. Right, so NO2 is 2x. That's squared. And then N2O4 is 0.047 minus x. Okay. Now, are we going to have to make any assumptions here? Well, let's look at it this way. What is K value? K is extremely small, right? Which means very little of this is going to be produced. That means X is vanishingly small. Right? So if we write this out as The K is this, and minus 8. And then our values are, let's go ahead and multiply that. 4x squared divided by 0.047 minus x. That's very close to 4x squared over 0.047. Why can I say that? Because with 10 to the minus 8 producing product, it's going to use up such a little amount of this, we can estimate this value here as this value. Okay. Otherwise, if we keep the x and we solve, we're going to end up with a quadratic. Okay. So this times that equals, I'm going to write 4 here, x squared. Did I skip too many steps? Okay. So let's take 4.66 exponent 8. This and 0.047 divide. So this is going to be 5.476 times 10 to the minus 10. And x will be the square root of that. 2.34 times 10. 5. So x is going to be this many moles, actually molarity. Right? And we need to determine molarity here, so 2 times x is 4.68 times 10 to the minus 5 molar. And this is 0.047 minus that value right over there. Which is essentially 0.047. Because look how much smaller that is. That's 3 orders of magnitude less than this. So when you round it off, you still get this value. Okay. So now that we've got molarity, we need to know how many moles that is. Right? What's the size of the container? 1 liter. Right? So if you got 1 liter and that molarity, the number of moles of this one equals 0.047. And for this one, in O2, 4.68 times 10 to the 5. Okay, so now we have the total moles of our gas, but notice what happens. When you add this one to that one, and round it off to significant figures, what do you get? Right? Our product is so small. So the moral of this story is, we could just as easily have said, based on this value alone, we know that vanishingly small amounts of this are going to be produced, which means the overall moles of gas in that container are essentially what we started with, right? So I could have skipped all this in here, but if I had, I wouldn't have been able to prove it to you. I would just been able to argue, but this actually proves that that's the moles you need. So we got moles, we got volume. We've got pressure is what we're looking for. And we've got temperature, which is minus 80 plus 273, which would be what? 1. Okay. And now we can calculate the pressure. All we need is P equals nRT. So the number of moles is 0.047. R, temperature, and volume. Okay. So I get 0.74. 0.74 atmospheres. Okay. All right. So let's see. We've got 20 more minutes. Which one should we tackle? Ooh, there's an explosion. Explosions are good. Have I covered everything so far?
So far.
Something else didn't come to mind in the process, is what I'm asking. This will be the last one. And then we'll look at our lab for today. Number 34. Okay. A sample of solid, what is that? NH4NO3. We don't have any farmers in here, do we?
Isn't that fertilizer?
Yeah.
Oh yeah, we was talking about that.
We don't have any terrorists in here either, do we? Ammonium nitrate. Oh, you don't have to be a terrorist. You could be a miner. AMFO, ammonium nitrate, fuel oil. They put a stick of dynamite in the base of the hole, then overpack it with AMFO, and it magnifies the blast 100 times. Okay. Let's see. So here's our reaction. O. This is actually not the reaction that occurs when you react with fuel. This is simply ammonium nitrate explosively decomposing into dinitrogen oxide, laughing gas, and water vapor. So at equilibrium, the total pressure in the container was found to be 2.63 atmospheres at a temperature of 500. Calculate Kp. All right. So I think we need a Well, maybe we don't need. If you assume total decomposition from that to that, which is probably true, then this total pressure, 2.63 atmospheres, is these two guys. So this is going to be, say, X atmospheres. This is going to be 2X atmospheres. Right? Because the molar ratio says that for every one of these, you get one of those plus two of those. And we also know that the total pressure is the sum of the partial pressures, and the partial pressures are proportional to the moles. So the total moles, the mole fraction here, will be the same as the fractional pressure. So we know this X atmospheres, and the total of those two is 2.63 atmospheres equals X plus 2X. All right, so we got an equation in one unknown, right? So we can solve it. That's 3X. So X equals 2.63 divided by 3, which is 0.877. Right. That means this one is 0.877. And actually, that one is the difference.
Where did the 3 come from?
1 plus 2.
Oh.
Okay, so if this is the pressure of that gas, and the total is 2.63, the pressure of this one is minus 7, which is 3, 5, 7, 7, thank you. 1. Okay, now we got our equilibrium situation. Just say Kp is the partial pressure of, actually, we won't have a denominator, will we? Because it's a solid. So we're going to have partial pressure of N2O to the first power times the partial pressure of water to the second power. So N2O is 0.877, and water is 1.753 squared. I get 2.70. That appears to be C. Okay. We covered most of the ground, I believe. So let me pause this for a second, and I'll be right back after the lab. Okay.
If we're going over the pre-aligned questions, do you want us to like write them down as well?
You can if you want.
Okay, because do we turn the pre-aligned questions with this into, because there's points on.
Yeah. It's kind of like a freebie. Okay. So this is going to be, let me just write a subtitle here. It's going to be Okay. There. All right. So we've got two types of equilibria that we're dealing with here. One is, actually three types. All right, so the three types we're dealing with is solubility. You can actually change the solubility of a compound by changing the equilibrium position. We'll also have complex ion equilibrium, similar to that the pink-blue thing we talked about earlier. And then we have acid-base. So those are the three foci of today's activities. Let's look at pre-lab questions. All right, so pre-lab. One says, what do we mean by a stress applied to an equilibrium system?
Maybe it's like how much stuff they put on it. Like
What if,
temperature and pressure.
right, you're going too specific, so I want a general definition. Suppose that you're vegged out and maybe watching a game on Saturday or Sunday, on Sunday. And you got your popcorn, you got your drink, whatever they have to eat, and somebody comes bouncing in the room. You're at equilibrium watching that game. Everything is just taking it all in. And here comes somebody bouncing into the room. They're providing a stress. There's y'all. Right. In layman's terms, stress throws off equilibrium. In other words, it causes a change. Stress is a change in the system. Okay. A change in the system that forces the system out of equilibrium. Right? It requires a response. Semicolon, just comma. Requirement. Requiring the system to respond to reestablish. Okay. Then the second part of that is give some examples. Actually, I answered the last part already in one statement. The stress itself is a change in the system that forces the system out of equilibrium. And then the last part of that question is, how does an equilibrium system behave? Requiring the system to respond to reestablish equilibrium. Those two parts. Now for examples. Okay, what type of stress could we apply to a system? This is just in general terms. It doesn't have to be to every equilibrium system.
More of a product, I guess. Yeah, or more of a, either more of a product or more of a reactant.
Right, concentrations. If you change the concentrations of either reactant or product, and it only has to be one of them, then the system has to respond. What's another possibility?
Temperature.
Temperature, okay. We'll force the system out of equilibrium.
You change the pressure, what it is, it.
Pressure. Now, how can we change the pressure? Well, we could change the pressure by introducing more reactant or product, right? But we've already covered that one up here. So how would we do pressure alone without introducing?
We have to have it in some kind of container, like compressive.
Right.
Like what?
Pressure.
Yeah.
Change of volume. Yeah.
Like the hot bottom line that we have.
I'm sorry?
Like the hot bottom line we have.
Mm-hmm.
Or something like that.
Okay, that was one. All right, let's take number two. How many of these pre-labs we got anyway?
There's one more.
Two. 1, 2, 3, 4. Okay,
Then we have
I may not do all of them. Pre-lab 2. Okay, say we have this system. Gas plus oxygen gas. And the product is F gas. Reaction's already taken place, we're at equilibrium. Now, this brings up a point. When you answer questions in this document, if you say, if the question is, which direction does the reaction move? And you say right or left. If you don't give me a reaction to go with it, I don't know which way is which, right? Because if you write it backwards, your answer could be exactly opposite wrong. So you got to give me a reaction. And when it says right or left, then I know which direction you're going. So for this one, we're at equilibrium, and we're going to add O2. Add O2. Since we have a reaction, we can say right or left. So if we add O2, which direction is it going?
we're gonna go left.
Go to the right, because there's.
Right, where's this? You're adding reactant, right? So it shifts to the product. Okay. Now B. Sulfur trioxide is removed. Remove sulfur trioxide. So if we remove sulfur trioxide, which direction is it going? Huh?
What? I feel like it keeps going right.
Mm-hmm. It is going to the right. Why?
It's-
Because you're removing that. Look at the, let's write the K for this reaction. All right, if that's constant, and you decrease this, what happens? What has to happen to that to keep this constant? Remember? Right, this has to decrease also. So that means that has to decrease. If you decrease this, you got to decrease that. A constant equals a quotient is a direct proportion. That is, if this one goes up, that one goes up. This one goes down, that one goes down. You can look at it that way too.
So that,
So it has to go to the right. Got to make some more of this to reestablish that K value. How about C? the pressure of the system is decreased. Pressure decreased. So if we decrease the pressure,
And the other side's going to decrease.
the key to a pressure change is how many moles of gas before and after. All right? So if you're making 1 plus 2 is 3 moles, and it's going to 2 moles, then if you decrease the pressure, say by increasing the volume, then you're making more room. And what the system tries to do is expand to fill that space with more moles. Right? So if we decrease the pressure, we increase the volume, then it's like it's sucking it over to this side, more moles.
It's going to like.
Yeah, it's going left. Because what is it doing actually? If you increase the volume and you've got the same number of moles to begin with, then you decrease the concentration. You decrease the concentration of both sides because they're in the mix together. But by decreasing the concentration, you decrease the concentration here more than you do there. So it compensates by making more gas. D. Okay. A very efficient catalyst is used. What does the catalyst do to an equilibrium?
It would make it react faster, which would cause there to be more product.
You are half right. Catalyst makes the reaction go faster, does not change the equilibrium.
That goes right.
No, doesn't change it at all.
No.
Doesn't change the equilibrium. Changes the speed that the reaction goes.
So do we write down speed here?
But if it goes faster, like if the reactants go faster turning into the product, wouldn't the product?
Okay, let's say we got a catalyst here.
Because to maintain the equilibrium, like both sides have to like be even. So if you have it going like making the product faster, how would it remain even?
Because it also makes reactants faster.
Oh, okay.
It goes, it
See, I
speeds up
thought
both
catalysts
directions.
only work on the reactants themselves, and then like it didn't affect the product afterwards.
No, catalyst goes both directions.
Oh, okay, all right.
Yeah. Because it look like this, let's just say it's like that. That's without a catalyst. And this is progress. So we have reactants here and products here. So this is the activation energy. Without a catalyst. With a catalyst, you go up here like this. Yeah. So the activation energy with a catalyst. So it affects both directions. I mean, if we want to go this direction, it takes just a little bit of energy to go up here.
Okay. Yeah, all right.
Now, if we were talking biochemistry, you would be onto something. Biochemical catalysts theoretically can do this forwards and backwards, but as a practical matter, they're more efficient in one direction than the other. Enzymes. And that's why most biochemical reactions have at least two enzymes, one for the forward, one for the reverse, and they are under cellular control. In other words, you could activate the forward one and not activate the reverse one.
That's how like our bodies function to produce like bone and stuff when we grow. There's some kind of like it's like a protein or something that gets injected in the bloodstream and then it causes the bones to grow. or causes the body to produce more.
Uh-huh.
And then there's another one that's like comes out to shut it off so that it stops doing it.
Right. In fact, they use two different cells to produce those enzymes.
Right.
One is the osteoblasts make the bone,
So that's like
and the osteoclasts
Yes.
destroy the bone. Yep. Okay, was that? Yeah, that's the last of number 2. So let's look at number 3. Explain why the solubility of a sparingly soluble salt represents an equilibrium system. Okay, let's say we have a salt. We'll just use the one that we're going to play with today. Sodium chloride. Let's do it this way. In solution, the sodium ions are in aqueous, and the chloride ions are in aqueous. And in a saturated solution, they are in equilibrium with that clump of sodium that's on the bottom of the vessel. We've saturated. It won't hold anymore. Any more you put in there, it's just going to combine, sink to the bottom as a solid. So that's our equilibrium situation. Sodium ions in aqueous solution at a certain concentration, in excess of that concentration, will produce the solid. So, with that being said, and with this formula, how do we explain solubility as an equilibrium situation? Well, actually, I should have written it the other way. It's better the other way. Like this. For our discussion, that's better. So how is this an equilibrium situation? Think about what's happening in equilibrium. What is happening in this equilibrium? I mean, is that it? Is it just sitting there? Like this clump sits here and these guys stay there and nothing happens. Remember the first day I talked about equilibrium? What did I say? Macroscopically, what do you see? Nothing. Equilibrium shows you nothing. Macroscopically. But what's going on microscopically? Forward, backward. This reaction, forward and backward, these two are furiously fast. They're just constantly going backwards and forwards. It just so happens that they balance one another at equilibrium. That's why macroscopically, we don't see any difference. Okay. So what does that mean? That means the rate of this forward reaction, and we'll use our rate expression sort of. The forward reaction and the reverse reaction. The K for those values, right? That kinetics formula. The K of the forward reaction is equal to, no, not the K, the rate. K is in there, but the rate of the forward equals the rate of the reverse. That's equilibrium. And you can describe equilibrium in terms for solubility systems, right? For complex ion formation, for acid-base reactions, or for a host of other types. These are the only 3 that we're dealing with today. So you just have to put it in words. Now, number 4, I'm gonna let you guys look that one up, because that'll take a little research. Looking up the IUPAC name, the proper chemical name for phenolphthalein. So what do I mean by IUPAC? I'll give you a little hint. I'll pull it out this way. IUPAC. This is International Union of Pure Applied Chemists. They set the ground rules, particularly for nomenclature. So if you're going to name a compound, you go to these guys to figure out how to name it unambiguously. Right? And I'll give you some warning. The phenolphthalein formula has carbon, hydrogen, and oxygen in it. Right? Carbon, hydrogen, oxygen. In a certain ratio. And the name is about that long. So you just have to do a little research, right? If you type in phenolphthalein IUPAC, or you type in phenolphthalein and you Google it, and you go to one of the sources, just look for the IUPAC name, and that'll be it. There's only one possibility. What's the other thing? The other thing is pH range.
So you guys identify the pH range in the name of it?
Yeah. The formula, the name, pH range for color change. Okay? And that'll answer number 4. Okay? So, it's 10:15. We're doing good, huh? 10 minutes. Supposed to start at 10:25. Since there's only 3 of us, it shouldn't take too long. We'll just have one group. And as we progress through, I'll make comments on the board.
Basically where it says observation, we talk about what happens when we add stuff.
Uh-huh.
And explanation, we explain why it happens.
Why it happens, and it may require writing a